Morning, everyone. Or most of you, I see people are still just appearing. So I thought that the first thing I would do would be go through the complex class exercise from yesterday. But before I do that, I'm very happy to take any questions that anyone's got, anything that's not clear so far. I don't know if Juan or Oliver have any announcements and such.
No, nothing.
So could people sort of put their hand up if they had any major problems with the complex exercise? Okay, in that case, I'll just have a look at this exercise briefly. I'll just, what was I going to do? I was just going to remind myself exactly what I said. About it. Okay, so let's just try and compile this. So obviously the compiler spits out a lot of complaints at us, and one of the things that you have to get on top of is learning to understand what the compiler means by all of these things, because in general the error messages that you get are going to be totally correct. They just may be unhelpful. Now things have got quite good in the last few years. They're much better than they used to be, but you still have to learn to read them in the way that the compiler is thinking. So here it's complaining on line 6 of the file complex.cpp, and it's saying that there's no declaration that matches this one. So let's look at the declaration here, line 6. So this is a kind of a getter type function, and here it's saying that it takes no arguments and it returns a reference to a constant double. And it's saying that there are some candidates, and this candidate defined on line 13 is a constant on the instance, but it returns a value of a double. Now, these declarations are clearly slightly different, and from the compiler's point of view, any difference is too much. So we need to make them agree with each other. Let's stick for now with what's written in the header. This may or may not be the best thing to do, but what this will do is it will return a copy of the real part. So if I save that and recompile, okay, it's still unhappy, but yep, and it's still unhappy because I forgot to add the const there, meaning that the instance that's being worked on is constant or unmodifiable through this variable. Okay, so that first one's gone, and now if we look at line 14, we're saying we've got a similar thing. So it's saying no declaration matches, but this time it's for the conjugate one, and this one is trying to compute the complex conjugate. So in this case, it's saying that the candidate is a member function of complex that can modify the instance, whereas the definition we've provided cannot. So computing the complex conjugate of a number should not modify that number, so the definition is the correct one. So we should correct the declaration instead. And we can repeat the process. I can actually find where the starting errors is. You'll notice that each of these times I'm going to the first error, dealing them with the order that the compiler complains. In part, this is because the compiler will often get very confused if you make errors, particularly things around like a missing brace or a missing semicolon. You can find that the last error is totally nonsensical, and it's only the first one or two that actually make any sense. So it's always best to tackle these problems first to last. Okay, in this one, we're saying that there's no matching call for this complex, attempt to construct a complex. And it's saying there's some candidates. So there's the default one, which is obviously not what we want here because we're trying to set it up with a particular value. And there's the this copy constructor. So there's no declaration of this thing. So we need to provide the declaration. So we need a purely real one. And we need a bit from both parts, and I misspelled that. Okay, so it compiled something. It compiled the main file. Now it's just downloading a library called catch. That's for a very common unit testing library. It's quite neat. You just need a single header file, which is why I've used it here. And then it's trying to compile the test program, and it's complaining a lot. So again, we need to look at the first error first to find out what's going on. And it's saying here that there's an undefined reference to the constructor for complex, which takes two doubles. So that's the one we just declared. We didn't define it. So let's provide the definition. If I could spell, that would help. So I'm just initializing the members, and then I don't know why that's doing it, formatting it that way. Initializing the members in the sort of member initialization list, and then there's nothing at all in the body. So there's multiple occurrences in the error message of that. Okay. So next, we should probably also provide an implementation for this one, since that's there as well. So let's do that while we're here. Okay, so the error is saying, warning, no return statement in function returning non-void. Okay, so that's quite a useful warning. That means we've forgotten to return something in the implementation of operator multiplication. So if we go to line 42, okay, so there's a hint for us about what needs to be returned. So we need to return a complex, and we need to set its real part to be the equivalent of this. So I chose some quite unfriendly notation there. I'm sorry about that. So it's the two real parts multiplied. And then the less the complex parts multiplied, the imaginary parts multiplied. And then for the imaginary part, we need A's imaginary times B's real, and A's real times B's imaginary. Please shout out if I make a mistake. That's always a danger with live coding. Oh, and I've made it, but not actually returned it. Silly me. Okay, so we've got a bit further. Where's my first error? Okay, operator subtraction, which I've not provided. So what's going on with operator minus? So I've declared that I have operator minus for these things, and I have unary negation as well. Okay, so operator subtraction is almost the same as addition. So let's just copy that and change the operation that's applied here. Oh, so something compiled. Let's see if this works. Okay, so we have a program that runs now, but it's failing. So it's saying that on line 32, when we're requiring that 1 be equivalent to 1, that's failing. So let's look at the test program briefly. Line 32. So 1 has been initialized to 1. That's perfectly reasonable, and we're just comparing it to itself. So that really should be correct. There's nothing obviously wrong here. So let's look at the implementation of operator equals equals. Okay. Can anyone spot the bug? Oh, I've got it. Yes. Okay. It's that's. Yes. Thank you. So I'm afraid I hadn't actually rehearsed doing this exercise before. Yeah, so I've done this at some, oh, okay, and there we go. Okay. All the tests pass, so I've produced something that approximates a complex number class here. Now, this doesn't have all the features you'd want if you were providing it for a standard library, but it might be good enough if you just needed something like this in your own code. Now, of course, you don't want to actually use this code because the standard library provides a perfectly reasonable complex number template class. However, you can always find cases where the ones provided in the standard library aren't quite right. For example, your problem might be better suited to representing complex numbers as a magnitude and an angle, and you could provide a similar implementation that implemented exactly the same interface, but for some reason, perhaps, if you often needed to know the magnitude in your calculation of these things, instead of having to do the square two numbers, add them and square root them, you might get a non-trivial performance improvement by providing your own implementation that stores its internals in a different way. So Matthew asks, why use curly braces rather than round parentheses to construct an instance? Now, this is mainly a style thing. There are a handful of cases when you require the curly braces to do this. So it's a stylistic thing. The cases where you have to use the curly braces are when you're doing things like aggregate initialization. And the reason that there's a school of style that says you should use the braces to initialize most things is to distinguish that you are calling a constructor. So this says to your reader, I am constructing here. I am not calling a function, because construction and function call are different things in the language, and it allows you to visually distinguish them more easily. So, again, this is one of these style things that's a sort of a more modern practice. It's certainly not required. Again, best to fit in with your code base and be consistent. But if you're starting a new project, I would recommend start using the newer style. So are there any questions about this exercise before I start talking about loops and containers and such things. So shout out if there are any, if you're just composing your thoughts. So I'll just start on this now. So we've really only talked about doing a single thing at once at the moment. And, you know, pretty much any simulation or analysis you're going to do, you'll end up needing to deal with many things, many data points, many atoms, many images to recognize objects in, whatever your use case is. So we're going to need some way to store these things. And the sort of the way the language wants to do this is with containers. And you've probably got some intuition for what a container is. So in C++, a container is a class type that holds objects of a uniform type. And it owns the objects that it contains. That means that by ownership, I mean if you destroy the container, you destroy the things in it. And importantly, the container provides access to these elements. And the way that you get this access and the performance of these operations depends on what the container is. So the standard library has 13 of these things, but I'm not really going to talk about any except a few of these things, which I list here. And let's just start going through them. So vector is the first one, and vector is unfortunately poorly named because it is not a vector in space or in the sort of mathematical vector space sense, but we're stuck with this name. It's stuck in the standard library. And what this is it is an array with a size that is determined at runtime, and hence you're going to be allocating memory for the data that's in it at runtime. And the elements within the vector are contiguous in memory. And what this means is that it is fast to jump to any particular element by index, and it's particularly fast if you want to run through them all in order because of the sort of the architecture of modern computer systems. Basically, when your CPU requests some data from main memory, this is slow. This is of order hundreds or thousands of clock cycles that your CPU makes. So to speed things up, the chips all include relatively large caches. And so when you request a single item from data from main memory, the chip is actually going to fetch a whole small chunk of that data into its cache. And that means that if you then access the next bit, it's already in the cache. So that is effectively instant. And as you keep running through your array, the hardware will notice that you are running through array. And so it will preemptively bring in the next bit before you need it into the cache, and hopefully make the whole memory traversal quite fast. So to use vector, you need to first hash include the vector header. And then to name the type of one of these things, you use a std vector, and you simply put the type of the thing that you want to contain inside the angle brackets. And so in this line, let's assume that getData produces a suitable vector for us, and reads it from disk or whatever it does. And then here to iterate through it, we simply say for int x colon in data, do this loop body. And in this case, we are pushing to std console out the value of it, followed by a new line. And then to end, we notice we have the loop body held within the curly braces here. So vector should be your default container unless you have a reason to do something else. So vector can do various things. You can copy and move it. So that means copy the whole vector, not a single element. And you can move the whole vector. And by move, it's really talking about moving ownership of the vector. And that move operation will only work if the element type is also movable, is no except movable for reasons. Okay, and so you can also access any element by index. It's random access. You can access element 0 or the last one at any time. I did not mention yet that vectors count from 0 like everything else in C++. You can resize these things. You can say, okay, set the size of it to 17, set the size of it to 20 million. And you can also pre-reserve memory. You can say, hey, vector, go and get enough memory to store 1 million of these things. And then you can start filling that up. And there will be no memory reallocation as you do that. You can insert elements and delete elements. And so just again, to reiterate, the vector owns its elements. So when the vector is destroyed, any contained data within it will also be destroyed. And it's worth stressing that a resizing operation might force the vector to get a whole new chunk of memory, copy your existing data into that new chunk, and then delete the old data. So Long asks about the no except thing. So no except, when you put it on a function declaration or a constructor, says this function will never throw an exception. And so what I mean by no except movable is that your class has promised that if you move it, it will not throw an exception. And we'll talk a little bit about this later. This is really the only time I want to mention exceptions. So something that you often have to do is build a vector. So how do you construct one of these things? So let's suppose that we want to produce a vector containing the first n prime numbers, where n is a user supplied thing. So what we do here is we first declare our vector, and we're going to call it answer for answer. And here we just use the default constructor. So if you just declare one of these things without initializing it or calling anything, this is going to call the default constructor. And in this case, what it does is it creates an empty vector that has a size of 0 and a capacity of 0. We're going to start our loop off with here we're going to say our first candidate prime is 2. And then while the size of our answer is less than what we want, we are going to execute the code inside the braces here. The first thing we're going to say is if, assuming that we have a function is prime that works, which will tell us if this is a prime number or not. So if maybe prime is indeed a prime, we are going to add it to the back of our answer vector. So pushback is the name of the member function that will append this value you give it to the vector. So this is like Python's list append method. And then we increment our prime number candidate and we go around the loop again. Now, obviously, this is terrible code, but it does illustrate the point. So pushback adds a new value to the end of the vector, and this is going to require reallocation of memory and copying the contents at some point. So can anyone think about how we might improve matters? Yes, exactly. So That is exactly right. So this would be the reserve member function that I alluded to here. Now, the full documentation for this is on CPP reference as ever. There's a fair number of member functions, each of which has a few overloads. Yeah. But the performance of this is not going to be so terrible as you might think. It's not going to reallocate every time you do this, because the vector will, in general, all the implementations of the standard library will do something a little bit smarter. They will, when you append to it, it will do something like double or the capacity of the vector. So you won't have to reallocate every time you do it. It will be something like log base 2 of the number could be. So when to use pushback versus in place back. So you use in place back when you want to directly construct your instance in the memory of the vector, and that means that you have to pass to in place back the appropriate arguments to your constructor. So there are times that when you might think using in place, it's a bit subtle when the right time to use in place back is. If you know you want to directly construct your thing and it's relatively expensive to copy, you may well want to in place it rather than push back. But for something as simple as an integer, where moving it, constructing it, and copying it are all exactly the same, there's no difference. There are a few decent blog posts that have appeared in the last year or two discussing this exact issue. So I would just Google it if you're ever concerned. As a rule of thumb, default to using pushback. And if you, through profiling or your intuition about what your knowledge that a certain type is expensive to copy in, might be better. But of course, if your type is movable, pushing it in from a direct construction is exactly the same as in placement anyway, so it's fine. Okay, so long, is that a good enough answer, Mohammed? Great. Long's asking about, we can always return an object. The compiler does automatic deep copy. Well, you can return an object when you are writing your function, as long as you control what the function returns, yes. The compiler will do a deep copy if that's what the type you're returning does. So you've got to remember in C++, you can always control these behaviors. So when are you talking about this particular function returning a vector? Yes, you can always return a vector because it's a copyable type. So if you're concerned about performance, don't be, because compilers are very smart. And we'll talk about how you can ensure that you help the compiler do its job later on today. Okay, so an array. So a stood array is a lot like a vector. It is contiguous in memory, and it contains types contains values of a uniform type. But the difference is that the size of your array is fixed at compile time. When you basically the size of the array is part of its type. And one difference in it is an array, a std array is pretty much an aggregate type. So this means you need to list the values inside braces when you're constructing one. So we would specify the type of it by saying this. So we could say that we want to work with std arrays of integers, and it's going to be 3 of them. And the syntax I've introduced here by Slate is a using declaration, which is basically an alias. It gives you another name to refer to a type, because std array of int 3 is not a particularly informative name. It doesn't tell you what you mean by that type. So let's suppose we want to talk about grid points. Maybe we're doing crystallography and we want lattice points, which are guaranteed to be integer coordinates. So we can create one of these points by just basically constructing it, but like I mentioned, we have to do aggregate initialization with the braces. So we've got some point, and we can do something like print the size of it, which is guaranteed to be 3, and this will be known at compile time. And otherwise, you can treat it much like a vector. You can access a member, you can put it in a for loop, and so on. So list and forward list are the slightly less commonly used. So both of these types are implemented as a linked list. So a list is a doubly linked list, which means you can go from one element to the next one or to the previous one. And a singly linked list or a forward list means you can only go through it forwards in one direction. And these elements are allocated into separate chunks of memory one by one at runtime. And so traversing this list involves jumping around in memory as you move through these. And you have to start at one end or at the other. But the advantage that they offer is that there's fast element insertion and deletion if and only if you don't have to go searching for the place where you want to do this insertion or deletion. If you already have a reference to the element that's going to get modified, this can be quite fast. So really, there's only a handful of cases when you'd want to use these. Why? Since it doesn't use contiguous memory, why use it? Because it allows fast element insertion and deletion. So for example, if you have some sort of list or queue type structure where you're going to be adding and removing from one of the ends a lot as you build some structure, and if the elements that are contained are expensive to copy and move, which is what you would have to be doing if you were using a vector or an array or something, this could be quite bad from a performance point of view. So what you might do is you might have this sort of construction phase in your problem where you're, perhaps modifying at one end, and it's going to be shrinking and growing, maybe growing more than shrinking as this process goes on. But then at some point, you're going to stop changing it, and you're just going to be accessing it again later. You could build it as a list or a forward list or whatever, and then convert it to a vector once you're done, and use that for the faster access that you'll get afterwards. So other containers that you might often use are set and map, which are associative containers. And these are typically implemented as sorted data structures behind the scenes. So what this means is that you have to provide a way to order elements. By default, this will use operator less. So for things like numbers, it's obvious what the sort should be. It's just standard numerical less. And set is typically just a set of is just the keys. So it's much like a Python set, except it's maintained in sorted order behind the scenes. And a map is a bit like a Python dictionary, but the keys are all of one type and the values have to be all of another type. So the two types, the types of keys and the values can be different. So for example, you could have a list of strings indexed by integers or whatever. And set and map both have unordered versions, which instead of using some comparison operation to sort things out, use a hash table. But in this case, you have to ensure that there is a way to hash these things. So you might want to use these if you've got a very large key space that is empty of values, and you're going to be looking up unpredictable values a lot, or frequently adding and removing these values. So there are other ones of these, but I don't really, you'll very rarely come across them in HPC type scientific computing code. So some guidelines. So this guy, Tony Van Eerd, did a talk entirely in rhyming couplets a few years back. And I liked these lines. So each container has its traits that define the places where they are great, particularly vector. You don't need a lecture, just use vector. Or more succinctly, when choosing a container, remember vector is best. Leave a comment to explain if you choose from the rest. Okay, so I think that is actually pretty good advice, and I've tried to adopt it myself. So if you're not using a vector, leave a one-line comment to your reader, who maybe you'll say, oh, you chose that. Okay, so loops. How do you go across a container or something else and do something to it? So the language really has three types of loop. A while loop, and then the next two are kind of two aspects of each other, but they are a little different. So you have your first a range-based for loop, and then you have a C-style for loop as well. So let's just go through these briefly in turn. So a while loop is quite simple. You have the keyword while, and then in parentheses, you have an expression that can be anything that can be convertible to a Boolean type, a true or a false value. So for example, an integer is convertible, a 0 is false, and anything else is true. So if we think back to that prime number computation we had a little bit back before, we've got the same, this is just reproducing that same code. We have our while loop, and inside here we are doing an inequality comparison here. So it's something a little bit more complex. It could just be a variable or whatever. And then this body between the braces is repeated until that condition turns out to be false, and then the loop will stop. Okay, so here we have a range-based for loop that we had before. So we've got some function called showData that is going to print the contents of a vector of integers to the console. So for the for loop, we have the for keyword, and then inside the parentheses, we have this syntax, which is a variable, or it can be a variable declaration, or just a variable name that's been previously declared. I would recommend, or in almost all cases, you're going to want to declare the variable here. So this variable x will only exist from the start of the parentheses to the end of the braces. So it's only going to exist for this bit of code. And then we have a colon after the variable, and then we have an expression that is going to be used for what to iterate over. So you would usually read this as something like for integer x in data. And this should look fairly familiar to the Python programmers there, except instead of the keyword in, we have a colon. And it's worth pointing out here that every time around the loop, we are copying a single element from data into a local variable x. So what we might want to do, in particular, if we want to modify this, I'll come back to that in a second, Marcelo. Let's say instead of just doing a read-only operation on our container, we want to modify it. So let's say we're going to double each element in our vector now. So we need to change what we're doing slightly. We say for integer reference x in data. And what this is going to allow is it's going to say that x is now of type reference to int. And every time round the loop, x will refer to the next element within data. And so we can modify it in place, and these changes are reflected in the data inside this variable data, which, because we've passed it by reference into the function, will be reflected in our caller. So we're going to be modifying that exact data in place. So what can you iterate over here? So the rules are basically anything, any expression whose type has begin and end member functions. And all of the standard library containers have these member functions. They have a begin and an end member. But as well as that, if your type does not have these things and you don't control the type or you don't wish to change it, you can provide overloads of the free functions begin and end. And if they accept just a single reference to your object, they will be called instead. No, I forget the project. I think they'll be called if there are not begin and end member functions. So this allows you to adapt types you don't control to use range-based for loops if that's a thing you want to do. And obviously, if you're writing your own custom container for some problem, you might well want to provide begin and end member functions so that it will work. So C programmers will be very familiar with this, but we need to make sure that you are aware of this, even if you're not coming from C. This is sort of the canonical form of a counting loop here. So what this loop here is going to do is it's going to say I is an integer, and I'm going to initialize it to 0. This happens on as you enter the loop before you've done any iterations. And then before you do an iteration, you're going to check this condition, which is I'm going to say, is I less than the data's size? And then at the end of every loop, this is the code that will be executed to go from one iteration to the next one. I'm going to pre-increment I, which means add 1 to it, effectively for integers. C programmers might be a little bit unhappy that I've gone ++i instead of I++. So C++ programmers will always by default use ++i rather than I++, unless they have a very good reason. And that reason should probably be explained with a comment. And the reason for this is that a post increment has on your own types, if you overload that operator, what that has to do is it returns a value, and that value is the value that the variable had before you increment it. So that requires a copy. And while the compiler is very smart and it may be to avoid doing the copy in some cases, it cannot guarantee it. So you should always make sure you pre-increment rather than post-increment. And sometimes this is the loop you need, but you should usually try and have a range-based for loop for the simple cases. You know, that's your default, and it's the kind of what you say when you say nothing approach. You know, the default communicates a lot to your readers, and you know, you need to learn these things from the idiom of the language. Yeah, worth reminding everyone, C counts from 0, and we are iterating over all the values that go up to but do not include the size of the array. Okay, so iterators. And first obvious question is, what is an iterator? So let's think about our C loop again here. And in this function, we're mixing up quite a few things. So we're mixing up the way in which we are iterating through the data, the operation that we're performing on it, and how we access an element. That's a reasonable question, Christoph. Do range-based for loops work with OpenMP? I honestly don't know. So a range-based for loop under the hood does get transformed into a conventional indexy loop. You'd have to read the OpenMP spec in detail for it. I honestly don't know. Sorry, I do some OpenMP, but I don't do a great deal. You might need one of the more modern ones. I know that the C++ support in OpenMP got a lot better with 4. Okay, so sorry, what was I saying? So we're mixing up things here. So we're mixing up the order and the way in which we're iterating through the data, what we're doing to it, which is kind of partly on this line, how we access it, which is this bit of that line. And we're also requiring that our data, the thing that we're working on, we're requiring that it supports random access because we're using operator square brackets to get element I, and not all containers support that. So this is the sort of old-fashioned C++ way of iterating through a container. So it's a little bit verbose. So we need to say that iterator has the type of the iterator type contained within a standard vector of integers. And we're going to initialize this to the data's beginning. Then we're going to have our carry on condition being that the iterator we're working on is not equal to the data's end. And then we're going to move from one iteration to the next. We are going to pre-increment the iterator. So in more modern C++, you can let the compiler do the typing for you and deduce the type of the iterator. So we're saying that it has the type of data.begin, and it's a value type. We want a value type because the iterator is a new object that we want to own and modify. So what have we got? Notable things. We've got, again, stress that we're using the pre-increment, because a post-increment you would have to return a copy of the iterator at the value it had before you did the iteration, and the compiler may well be able to avoid doing that if you turn on optimization with -02, but it might not in some cases, so don't. Then in here we are using a comparison operator, so that means that the iterator has to have a not equals comparison operator defined for it. And here we are using operator star to get at the value point referred to by the iterator. So this star thing is called the dereference operator in this context, and it basically means go and get the thing that this iterator is referring to. So these iterators are just class types with a defined convention about what members and operations they need to support. So if you want to implement your own because you're doing it over your own custom container, or you want to iterate over your data in a particular different fashion that's not simply one to the next. For example, you might want to implement an iterator that will iterate over all the points in 3D that are around a particular grid point or something like that. So exactly which overloads, which member functions and overloads you need to provide depend on exactly what category of iterator you want to support. And again, C++ reference will tell you exactly which ones this needs to be. If you want to just have a forward iterator, which is a fairly simple type, it lists all the things that you need to have. So you need to have well-formed increment things. And it says it also has to satisfy, input iterator, which says things. It has to have a not equal operation, a dereference one, which will give back a reference to the pointed to referred to value. You need to be able to plus it, and so on. But yeah, these are the key ones. Dereference, pre-increment to go to the next one. Assignment, you need to be able to bind one of these things to a name. And inequality comparison, you need to be able to tell your user when you're done. So, maybe I think maybe my slides have got out of order. This maybe should have come in after I introduced the map container as a use case for when you might want to use it. Sorry about that. I'm just going to write down that I need to fix that. Sorry. So, imagine if you're doing some sort of structural parallel simulation where each process might own some part of this domain, which looks like it's, some sort of airliner. So the blue ones all belong to one plane, the yellow one processor, the green ones to another, and so on. And to do this simulation, perhaps each process needs to communicate some information about the stresses and displacement of the points along the edge to its neighbors. So after you've started up all these processes and read in the domain, you might have some code that's a little bit like this. You need a map from integers to some sort of object that is going to communicate across the boundary with the other ones. And you could call that rank2coms is going to have a type of a map from integer to this boundary com object. We're going to loop through all the ranks, so the ID numbers of each parallel process, going from 0 up to the size. And if the current process shares a boundary with that other rank, I'm going to create one of these boundary com objects in some way, and I'm going to store it in the map. So I'm going to say that the map, square brackets, a key value equals a value. gosh, that was a mouthful, value. And then later on in your code, you can iterate through this. You can use, if you're lucky enough to be using C++17, you can use this much nicer syntax where you can just list in square brackets the two parts, and it will unpack from the return the key and the value separately to iterate through this, and then you can use this boundary com object to send some local data to the other rank. The square bracket thing is called structured binding, and it's pretty similar to Python's tuple unpacking, although of course there will be some extra stuff to deal with because it's C++. Often it will just work for you, but CPP reference will have all the gory details. Is there something similar to zip in C++20? So remind me, zip takes two pairs of iterables and maps, a pair of iterables and maps them into an iteration over pairs. So yes, we'll talk about this when we talk about algorithms. Killian has checked the OpenMP standard for us about. So you need to be in OpenMP 5.1 to use range-based for loops. Yeah, sorry, I'm not surprised that it is supported in some cases because the specification requires that a for loop, a range-based for loop, is equivalent to a particular type of C-style loop under the hood. Okay, so there is an exercise to start using some of these containers, which is in the repository under exercises containers, unsurprisingly. And there's a few little instructions. It's very, very brief. Hopefully it should be fairly self-explanatory. Where's my slides gone? You can take the same approach as before of just try and compile it and see, fix the errors until it runs the tests successfully. So I'm going to go and get myself a cup of coffee and then come back and answer any questions people have about the exercise. I suggest you get yourself, have a wee break and then get on with the exercise, or start that, get a bit frustrated, get you a coffee and have a break and then come back. And I will start talking about it properly again at 11:15, I think. Unless there are any questions right now. Great, go ahead. Oh, that's the wrong one, sorry. Containers. Sorry, I had the complex the class slides up from before when I was just refreshing. Oh, okay, so asking about 17. You can use 17 if you want, yes. Let's see what the makefile uses. Yeah, just because 17 makes the access of maps and stuff. So the structured binding syntax, which I'm using here, is a C++ 17 feature. It's not available in 14. You would have to take the iterator. You would end up getting a stud pair of rank and the value type if you were to do it, and then you would have to go, pair dot first or pair dot second here, which it's just untidy. Whereas here you can write what you want, right? You can write what you mean because you don't care about iterating over pairs. You want the key and the value. No compiler and standard library fully support C++ 17 yet. Sorry, 20 yet. So in my opinion, we need to wait another major compiler version. Actually, I think that might not be true. I think GCC 11, they claim that they have finally got there with C++ 20 support, although I'm not 100% sure that's true. I suspect we'll need to wait until they've done a point release before it actually works. The other issue is, of course, that most C++ out there does not use C++ 20. I mean, it's a vanishingly small part, and so most of the code you see is not going to be C++ 20. My default for starting a new project today would be 17. But I think anyone writing C++ seriously these days needs to be able to deal with 11 and newer. If you're lucky, you can avoid the older stuff.